This project has been a real fun effort in trying to take a heritage booster that had many, many years of reliability and great performance and evolve it into something bigger and better.
When we first undertook this design and qualification for the new booster, part of the mission was to make the booster more affordable and more modern, and of course it had to be completely redesigned for a new mission. It's a larger booster, and the mission profile is sufficiently different to where pretty much everything on the inside of the booster is different. There's well over 1,000 individual processes. Working with our customer, we were able to identify several hundred areas of improvement.
We've got totally new avionics on this vehicle versus what we had on shuttle. It's state-of-the-art. We've taken that avionics and actually tested in development units in a full flight configuration and are about to enter some qualification testing with that system. But in this particular test, we will actually control the thrust vector control system with the flight avionics.
The old shuttle program utilized a rubber insulation between the case segment and the propellant that contained asbestos, and so we selected a fiber called PBI, which is used widely in the fire protection industry. Developed a new rubber formulation and ended up with a rubber that is actually higher performing than the previous material, which allowed us to remove a fair amount of insulation and replace it with fuel and get a little bit more performance out of it. So not only is it environmentally friendly, it's a higher performing material and a higher performing rocket.
Structurally, we've had to make some changes. The aft attach point of this booster, in order to accommodate the structural configuration of the SLS vehicle, has been moved several feet aft. And actually, this QM1 test will be the first test in a static configuration that we've done with that actual SLS attach point in place.
We had to design a new core and a new propellant grain inside the fuel that's inside the rocket. Part of that required us to design and manufacture all new tooling that forms the inside of the motor. We had to redesign our nozzle because we have a different performance, different things going on inside the motor, and so a large portion of the nozzle was redesigned.
Also, we've had a major effort over the last 2 years to try and improve the affordability of this vehicle, because the intent here was not only to have a higher performing vehicle, but to have one that actually costs less. And we believe we've achieved that, and this test of QM1 will be evidence of that culmination.
So we are getting ready to static fire the QM1 static test motor. It's a full rocket booster. It's made of 5 segments pieced together, and that's important as we've added another length of a segment into this booster to make it bigger and better. A lot of planning and work is done ahead of time as we design these rocket boosters to get the propellant geometry just right. We know at any given time during the burn of that motor what the thrust is and what the profile of the pressure is inside that motor. So with the new thrust profile for the SLS boosters, we've added an extra fin and changed some of the geometry of our propellant surfaces so we can burn more propellant at the beginning of the test, or beginning of the rocket firing. To get a solid rocket booster to burn, we have an igniter at the front end that is like a small rocket in itself, and it shoots a flame 150 feet down this entire rocket booster and ignites all the surface of the propellant all at once. Once you ignite a solid rocket booster, it can't stop it. You don't flip a switch to turn it on and off. At the same time, you can't turn a knob to increase your thrust or decrease your thrust. That's why it's important to design this beforehand, so we can get the amount of thrust we need at each point during this 2-minute burn to reach the maximum thrust at given time points that we need. At the beginning of the burn is when we have the most thrust, about 3.5 million pounds of thrust that we maintain for about 25 seconds. It takes just over 2 minutes of rocket firing for the propellant to completely burn out. And the propellant is burning really fast. It's got a certain rate that it's burning, but it's burning from inside out. So as every second goes by, it's like one layer of that propellant is essentially being peeled away and shot out the end of that rocket motor. And as this propellant burns and begins to create this mass that we are projecting out of this rocket, we are creating the thrust that we need to carry humans and astronauts and more weight into space.
T-minus 40 seconds. Pad flush is on. T-minus 30 seconds. Minus 25. Minus 20. minus 15. T minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, fire.
We have ignition of NASA's Space Launch System 5-segment solid rocket booster.
Activate head-in CO2.
CO2 activated.
Activate quench tool command forward and aft CO2.
Activated. T plus 165 seconds. High-speed data operator stop recording.
The full 2-minute test has concluded.
High-speed recording.
Now the carbon dioxide quench arm pumps 31 tons of CO2 into the booster. The carbon dioxide quenches any burning of the insulation without damaging it to preserve the state it was in during the test. This allows the team to get the best data about how it will perform in flight. There's quite a bit of action remaining for the teams here as they ensure the test area is safe and the data are recorded. Following motor burnout, the chamber will be sprayed with 2,300 gallons of water per minute on the underside of the case to help cool it down. This will cool the chamber from 1,000 degrees Fahrenheit to 300 degrees Fahrenheit.
Avionics engineer, verify that the Celestic has finished saving the log files.
In work.
Roger. Redline monitor operator, transfer the log file to the local computer.
Roger, in work.
Roger. Bus monitor operator, transfer the data files to the local computer.
In work.
T plus 4 minutes.
Redline monitor files have been transferred to the computer.
Roger.